Let's go through the derivation process of how we can start with this differential equation, and during the process we're going to apply the initial condition for this particular circuit, and we'll arrive at the charge as a function of time and the current as a function of time. So this is the circuit we have. If you haven't seen the video of how we got this equation, then go back and do that and then continue. So when you put the current as dq by dt, you get this differential equation. Now, how can we tackle a differential equation like this? Well, the strategy is going to be to try and bring all the q on one side and all the time on the other. So the first thing, let's just bring this r dq by dt on the other side. So you have r dq by dt, and then you have epsilon minus q over c on one side. And let's multiply by c on both sides. So you multiply by c here, you get r times c. You multiply by c here, the c goes, and this becomes epsilon times c. And then put all the q on one side and all the t on the other. All the blue on one side and all the red on another. So dq, when you divide by this, dq divided by this, you get all the things that have q on one side, and then multiply by dt and divide by rc. You put the constant with the time on one side. So why is this important to put it in this way? Because the next step, you can then integrate both sides, and then you'll be able to find q as a function of time. Before we integrate, let's just make a simple change of variables. Instead of having epsilon times c minus q, we can just call this a new variable s. That means when you take the differential of s, ds, it's minus dq. Now I can then remove this dq and write instead of it minus ds. And I can remove this and replace it by s. So this will make it a bit easier when you come to do the integration, because the integration of ds over s is just simple to do. So I just put it this way so to make it very clear. So we have now minus ds over s and dt over rc on the other side. When you integrate both sides and you multiply by minus 1, multiply by minus 1, this goes. What's integration of ds over s? Ln s. And what's the integration of minus dt over rc? It's minus t over rc. But then you have to add a constant, an arbitrary constant. So we can then substitute with this value of s that we defined, and then you get this. So now I have a relationship between q and t, and the next step is to try to identify what this constant is for this particular problem. This constant could be any value, and if you put any value for the constant, the equation will be satisfied. So we want to find out the constant a for this particular problem. So to do that, we'll use the initial condition. We have the initial condition that says when you put q equal to 0, the q equal to 0 when the time is 0. So when you put t equal to 0, this term goes completely. When you put q equal to 0, this goes. So we have that ln epsilon times c is equal to a. So now we found the value of a for this particular initial condition. So we have now that for this particular condition, the value of a is this value. Okay, let's substitute this a value into the equation. We get that. So when we write down this equation in this form, we have to put under a parenthesis or whatever, that where this equation has been solved for this particular initial condition. Now, the next thing is just some acrobatics. Just take the ln minus this ln, and you know that ln something minus ln something is the ln of something of the ratio. So we can write this as ln that over that equal to minus t over rc, and we have this initial condition. Again, it applies for this particular problem. Now the next step is to take the exponential of both sides. What's the exponential of the ln of anything? It's that thing. And what's the exponential of minus t over rc? It's e to the minus t over rc. So now we've converted the equation into an easier form, because in the end, what do we want? We want q in terms of time. So we can just simplify this. If you multiply both sides by epsilon times c, and then you keep q on one side and bring the other term on the other side, you'll get this relationship. So q as a function of time is equal to epsilon times c times 1 minus e to the minus t over rc. And that's the equation that we had actually in the previous video. This was the equation we wrote down. So this is how you arrive at that equation. And this equation satisfies the initial condition that when time is 0, the charge is 0. So now let's get the current. Well, the current is dq by dt. So if you take the charge as a function of time, I just multiplied in with epsilon c, the derivative of the constant is 0, and then I put the minus epsilon c as it is. The derivative of the exponential is the exponential, and then you have to take the derivative of what's over here, which is minus 1 over rc. So this is what you have. The minus and the minus will cancel. The c and the c will cancel. You get this final result, which is the result we showed before. So that's how you would get the current. So to conclude the summary, this differential equation, subject to this initial condition, has this solution. And it's very important to write it this way, because if you just say that the solution is this, you need to remember that this is a particular solution for this particular initial condition. You could have other solutions if you had a different initial condition. So this is particular to a very specific problem, that when time is 0, the charge is 0.